From last time we talked about kinetics. Kinetics is the study of reaction rates and factors that affect them. And we'll really be exploring one of those factors today. Before we do that, I just want to finish up the last piece of the lesson from last time. We learned how to write rate equations and we learned how to solve them, and that's what you saw in your do now, which was just that problem in your notes. But you also can determine rates from data alone, just a data table, very similar to getting the slope of a line or just looking for the change over time. And that's what we're going to look at here. This will be very straightforward for you. You can determine the rate at which a reactant is consumed, because we know reactants are used up as the reaction goes from left to right, or products get generated. So you can calculate them from data alone, and you can calculate this rate of change over time intervals. And that's what we're going to do with the data table shown here. In addition to calculating rates for intervals 1 and 2, or you could have even more intervals, which you'll see in your classwork, although on the quiz I kept it very simple like this. You can then compare those rates and see if they're the same, see if they're decreasing, see if they're increasing. Because what we find in chemical reactions is typically they start off slow and then they speed up, and then they'll probably slow again, or they'll reach some equilibrium point. And we'll talk about equilibrium in the next chapter. They really go together. So in regard to kinetics and equilibrium, we're going to do those two chapters together. You'll get a quiz on each chapter, although your quiz on kinetics is a partial quiz. It'll cut off where we finish up today. And then you'll be tested on both chapters together. Don't think either chapter is that difficult, but when you put it together, it's just a lot of material. In any event, it says calculate the rate of change for each interval from the data below. Is the average rate constant over the two intervals? I'll show you how to do that. If it isn't, does it increase or decrease? And we'll walk through all different scenarios. You have a chemical reaction shown here. You can see the concentration of chlorine gas over time. What information from the data table tells you that chlorine is a reactant? Its concentration is decreasing over time, and that's because reactants get used up. So if I gave you a product such as sulfur, its concentration would increase over time. So that's one observation you can make. So chlorine's concentration is decreasing over time. And we can determine the rate at which chlorine disappears over time doing the following. We know that we can write rate equations where we have rate is equal to -1 for reactant chlorine over its coefficient, change in concentration of chlorine over the change in time. And for these types of problems with data tables, they typically give you a coefficient of 1. It just makes life easier. If I want to know the rate for interval 1, I'm going to say rate 1 for interval 1, and that's going to be -1 over 1, change in concentration of chlorine over the change in time. So chlorine, in the first interval, you have 3 molar left, but you started with 4 molar, so you're going to subtract those. Very similar to getting the slope of a line. 25 seconds minus 0 seconds. So I've basically taken that second data line and I've subtracted the first data row, if you will, from it. And that's going to be negative times -1 molar over 25 seconds, and that's equal to 0.040 molar per second. So that's the rate at which chlorine disappears for the first time interval. The second one you'd set up very similarly. So you'd have rate for the second interval is negative 2.00 molar minus 3.00 molar, 50 seconds minus 25 seconds. That's also 1 over 25, so that's going to be the same. And from the example I've given you here, the rate of consumption of chlorine for both interval 1 and interval 2 is 0.040 molar per second. So in this case, the rate is constant because the rate for the first interval is equal to the rate of the second interval. And I'll give you some examples where it's not.
Would a question like that be on our test?
Quiz. Just a baby little quiz question. Grossly similar here. I probably use the same equation just to make it easy. I just want to give you a couple different scenarios then, and you'll see 2 classwork problems just for some additional practice. Let's say that rate 1 is greater than rate 2. For example, 0.060 molar per second compared to 0.04 molar per second. So what happened between the first interval and the second? Did the rate decrease or increase? Decreased. So this would be an example in which the rate decreased because the rate of the second is less than the rate of the first, or the rate of the first is greater. It doesn't matter how you do it. In contrast, let's say that you had 3 rates. And let's say the rate of the first is this, and the rate of the second is this, and the rate of the third is this. What's happening to the rate here? It would be increasing because the rate of the third is greater than the rate of the second, etc. And in your classwork, just so because you're going to have some classwork to do over the weekend, this way you know what concept goes with what problem, you'll see 2 little questions like this in 3 and 4, equally as straightforward. And your denominator doesn't have to be seconds, it can be seconds, minutes, etc. Now in these particular examples, when we were dealing with rate, we were looking at the change in concentration over the change in time. And so our unit was molar per second or molar per minute. Sometimes you don't measure the change in concentration. For example, with gases, you can look at changes in volume or changes in pressure. We're not going to do that at this level, so we're not going to go into it. We are going to do 2 colorimetric assays in the lab, the next 2 labs. The lab on Monday, Tuesday, deals with an iodine clock reaction where you will have a clear solution, you will mix it with another clear solution, and you'll measure the time it takes to turn blue-black. And so you also can look at how long it takes for color to change. And at a higher level of chemistry, you could determine concentration from that, but we're not going to do that at this level. So this section right here, we're not going to go into. I mentioned some of it, but you won't be assessed on that, so don't worry about it. All right, our real focus today is going to be on factors that affect reaction rates. And what you're going to see in regard to factors that affect reaction rates, we're going to be looking at concentration. And we're going to spend a lot of time on concentration. And that's the one we're going to look at in the laboratory as well. And we'll come back to that in just a few minutes. Surface area also is a factor that affects reaction rate, and we'll talk more about that after your quiz on Thursday. Another factor that affects reaction rate is temperature, and we'll talk about that one on Thursday as well. Our focus today is going to be on concentration, although to understand why these factors affect rates of reaction, we need to understand something called the collision theory. And I don't think there's ever been a better year than this one to talk about an effective collision, where 3 of my students in 3 different classes have incurred concussions this year. So, sorry. I won't embarrass you much. No, I'm just kidding. I would never do that. The collision theory states that chemical reaction rates depend on effective collisions between reacting particles. In order for a collision to be effective, the particles must hit each other hard. So they must have enough force. In addition, those particles must be oriented in such a fashion that they hit one another in the right spot. So, can I put you on the spot? Sure, why not? When you got your concussion this year, clearly to incur a concussion, you'd have to hit your head very hard, correct? How hard did you hit your head? Pretty hard. So how did we do this? Somebody else's elbow to your head? So he must have hit you really hard. Force. In addition, if a different part of his arm, and that's relative because his shoulder could have caught it too, although he would have had to have been much taller than you. But with his elbow, it had to be positioned in such a way that it hit what part of your head? Right over, and actually with the head, is there like one spot better than another to get a concussion? I don't know. Like here versus here? I think you could get a concussion hitting any part of your head, couldn't you? Yeah, I think so. But in any event, your head and his elbow had to be oriented in such a fashion that it was just a perfect little hit. Poor you. I'm sure he was fine. Did he break his elbow? Nope, see, it was an effective collision for him. Well, maybe it was, but no. In any event, force and orientation, critically important. Here's another example. Not recommended that you try this at home or you have your little sibling do this. Please don't do this. If you wanted to give yourself a concussion because you felt bad for your friend who had one, you could run into the wall head first. Now, you'd have to hit that wall pretty hard, right? And you wouldn't want a lot of padding on that wall either, because if you did, then the force might not be great enough. In addition, at first you might think it was something creative, but then you guys are very intelligent. You'd probably realize it isn't the greatest idea. You'd probably chicken out at the last minute and either turn to the side or maybe put your arm up. And then you probably could dislocate your shoulder, which hurts like crazy, or you could break your wrist, which also doesn't feel especially good. You need to hit hard, and the molecules need to be oriented properly. And you can see this orientation and force aspect here. Oh, really? I just clicked one little button. So here's your chemical reaction shown here. This is a decomposition reaction of nitrosyl chloride to generate nitrogen dioxide and chlorine gas. Shown in these two panels are two collisions, one of which is unsuccessful, one of which is successful. In the first collision, these two molecules hit each other hard. But if you look at your products, you want to generate chlorine gas. This one is unsuccessful because the two chlorine atoms are not positioned in such a way that they can link together. So this collision is not successful, and you basically go back to where you started from. In contrast, when we rotate this molecule 120 degrees, this chlorine atom now is positioned so it hits this chlorine atom. These two hit, and a bond starts to form between them, and this bond starts to break. And we'll talk more about this activated complex after the quiz. This is going to be a successful collision because not only did you have enough force, the molecules are oriented properly, and you get your desired products. The collision theory helps explain why these factors of concentration, surface area, and temperature affect reaction rate. So anything that increases the likelihood of an effective collision will increase reaction rate. And you always explain why these factors affect reaction rate through the collision theory, which we'll come back to when we talk about those other factors. Now, what we're going to focus on now is one of those factors, which is concentration. Generally speaking, an increase in concentration of a reactant will increase the likelihood of an effective collision, which increases reaction rate. Not always, but usually. There are a few instances where it doesn't. Let's say, for example, that you're all running around the classroom blindfolded, and an effective collision is ramming your shoulder against somebody else's shoulder. The likelihood of an effective collision in this class with 29 kids, I'm not playing, is relatively low. You're not all the same height, and there aren't that many of you. And if we moved all the desks over, you probably wouldn't hit each other that much. But if we invited every class on the floor in here, and you were all running around, the likelihood of an effective collision then would be much greater. So increasing the concentration increases the likelihood of an effective collision, increase in reaction rate. To better understand how concentration affects reaction rate, chemists have derived rate laws, different from the rate equations we wrote earlier. So be careful, we'll point those similarities and differences, and reaction mechanisms. Reaction mechanisms are a little more complicated. We're not going to go into them in honors. You'll see that more at the college level. But we are going to learn how to write rate laws and how to interpret them. It is extremely mathy, and you should be very good at it because you're very strong in math, especially the math you're going to see here. For example, 2 squared is 4, 3 squared is 2 to the 4th is? Really? That I don't even know how you came up with. 2 to the 4th is 16. 3 to the 3rd is 27. 3 to the 0 is? Anything to the 0 power is 1. 4 to the 1st power is 4. So we're just going to play with baby exponents, and you'll be solid there. A rate law is an expression for reaction rate. It's a function of the concentration of one or more reactants. One or more reactants. So you don't have products and rate laws. Only concentrations of one or more reactants. A rate law for an equation that has one reactant only, for example, reactant A forming reactant C, highlighted in yellow here is a rate law. It always starts rate is equal to. K is a proportionality constant, and other than putting the K in this year, you don't need to worry about it. Times the concentration of reactant raised to some power. N is the order with respect to A. N helps describe how altering the concentration of A affects the rate. N can only be determined from data, never, ever, 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 ever from stoichiometric coefficients of full balanced equations. What we're going to learn how to do is interpret rate laws, how to write them, how to figure out what that exponent is and why. And in the first half today, we're going to write very simple rate laws, and then in the second half today, we'll write more complicated rate laws. But if you practice this, you'll be extremely strong at this. The kids like it, they think it's puzzle-like, and once they get it, they think it's very easy. Now, n typically is a small positive integer, 0, 1, 2, 3, 4, 5, 6. If you get an n of 10, you probably made a mistake. N can be negative, and it can be non-integral. So it can be a fraction, but I'm not going to give you those at this point. So for your purposes, n typically will be 0, 1, 2, 3, 4, 5, etc. Before we learn how to write rate laws, I want to show you how to interpret them, and then I'm going to show you how to write them. There's a lot of information written for A, B, and C, and rather than read through that, I'm just going to give you examples so that you better understand what's being asked. For example, in A, it says when n is 0, the order is 0 with respect to that reactant. So n is 0. We said that a rate law looks something like this, where A is my reactant raised to some power n. If n is 0, then my rate law, it's a lowercase k, that's why I did a little lowercase script k. A would be to the 0 power. If the concentration of A is doubled, I want to see the effect on the rate if the order is 0. I have rate is equal to K. Instead of putting A in, I'm going to put a 2 in, because if something's doubled, it's going to be 2 times what it was. And 2 to the 0 is 1. And so if A is doubled, there's no effect on the rate. When it's 0 order. N is the order with respect to A. N here is 0, that's 0 order. What if A is quartered? For a 0 order reaction here, I'll put in 1/4. What's 1/4 to the 0? 1. Is there any effect on the rate? No. So this is one of the instances where when you increase the concentration, there's no effect on the rate because it's zero order. Just hang tight for a sec, you'll see the other ones. Let's say n is 1, first order with respect to A. So rate is equal to K, A to the first power, that is first order with respect to A. Now let's say if A is doubled, we want to look at the effect on the rate. We've got rate is equal to K. I'm going to replace the A with a 2 because I doubled it. What's 2 to the first power? 2. So the rate doubles or increases by a factor of 2. Let's say concentration of A is quartered. So I would have, I'm going to move this down one because it got too tight. Rate is equal to K, 1/4 to the 1. What's 1/4 to the 1? 1/4. So you can say the rate is 1/4 what it was, or the better statement would be, or decreases by a factor of 4, which is the reciprocal of 1/4. So when you get a number less than 1, the rate decreases by a factor of the reciprocal, and we'll do quite a few like that, so you'll start to see it stick. And let's take a look at second order now. And again, this is in your notes. I'm just trying to write it out in a systematic format so you can see it mathematically. Let's say n is 2. So now we have rate is equal to K, A to the second power. That's second order with respect to A. Let's say if the concentration of A doubles, we've got rate is equal to K. 2 squared is 4. So the rate would increase by what factor? Four. 2 squared is 4. Let's say if the concentration of A is quartered, then we've got rate is equal to K. 1/4 squared is? What's 1/4 squared? What? Really? 1/16? Now you get a number less than 1, so is the rate going to increase or decrease? Decreases by a factor of what? What's the reciprocal of 1/16? 16. And that's how you interpret rate laws.
Pretty much it's just the factor is going to be whatever the new answer is.
If you have a number less than 1, you're going to say the rate decreases by the reciprocal. If you have a number greater than 1, then the rate increases by that factor. It'll be 4 times what it was. All right, the key thing you want to be able to do when you walk out today is write rate laws. It's going to look hard, but you're going to be very good at it. And we'll do more of this interpretation with each rate law we write. So we want to learn how to write rate laws. The first example is done for you, and we'll walk through several together so you can see it. Once we get the beginning done, we'll take a little break, and then we will do the more complicated ones, and you'll have to practice those over the weekend. You have an equation in which 3 moles of A are converted into 1 mole of C. Reactant is A, product is C. What's shown here are 2 experiments. The concentration of A from experiment 1 to experiment 2 does what? It increases by a factor of? Is it doubled or tripled? It's doubled. The rate, and that's going to be the rate of formation of C, goes from 1 molar per second to 4 molar per second. So the rate increased by a factor of 4. 4 divided by 1 is 4. So when I doubled A, the rate increased by a factor of 4. So 2 to what power is equal to 4? 2. Let's work it slower so you can see it. If we compare these 2 experiments, I'm going to look at the concentration of A in experiment 2. I'm going to compare it to the concentration of A in experiment 1. I'm going to raise that to some power n. And I'm going to compare this fraction raised to n to the 2 rates, rate 2 and rate 1. So I'm going to plug in experiment 2's concentration, experiment 1's concentration to the n, rate 2's quantity to rate 1's quantity, and then I'm going to solve it. 0.4 over 0.2 to the n is 2 to the n. 4 divided by 1 is 4. N is equal to 2. So it's second order, and this is my rate law then. I always write rate is equal to K, concentration of the reactant, raised to its n, which is 2. Some of the kids asked, well, what do I put on top? How do you know? Doesn't really matter as long as you're consistent, but sometimes kids really don't like fractions. So put the larger concentration on top, which is from experiment 2, and therefore everything from experiment 2 goes in the numerator. If the concentration of A is halved, if you put a half here, what's 1/2 squared? 1/4. So this number is less than 1. Does the rate increase or decrease? Decreases by a factor of the reciprocal, which is 4. And that's what's written there. If the concentration of A is tripled, I'm going to put a 3 here. 3 squared is 9. So the rate increases by a factor of 9. Let's take a look at one from scratch. It's on the screen here. I'm going to work it on my paper. You have it in your notes, and we'll work it slowly so you can see how to do it. We've got 4D being converted to 2F. Some of you may see it very easily, what the order is. Others, it may take a little more work. what you're looking at here is you have two experiments. Which concentration is larger, 0.4 or 0.2? 0.4. So that's what I want to put in the numerator then. Now you don't actually have to show me this piece right here, but I do need this piece. I'm going to show both pieces on this just so you have a reference point, but I'll make it clear what I need to see. So to figure out the order with respect to D here, I'm going to have the concentration of D in experiment 2 over the concentration of D in experiment 1. I'm putting the concentration of D in experiment 2 in the numerator because the quantity is larger. And that's going to be raised to the n. And I'm going to set that equal to rate 2 over rate 1. We've got 0.40 molar over 0.20 molar to the n. And we've got 8 molar per second over 1 molar per second, and that's 2 to the n is equal to 8. So what's n? N is? Garrett, what's n? 3 is correct. You're writing a rate law. You write rate. What letter do you put after the equal sign? Lowercase k. Concentration of the reactant raised to the third power. So third order with respect to D. Now it asks you two questions. It says if the concentration of D is halved, put a half in. What's 1/2 to the third power?
1/6.
No. 1/8? Is this number less than 1? Yes, so the rate decreases by a factor of what? 8, the reciprocal. The other thing says if the concentration of D is tripled, so it would have put a 3 in to the third power. 3 to the third is 27. So we're going to say that the rate increases by a factor of 27. And that is how you write rate laws when you only have one reactant. Once you have the basis for this, we can write rate laws with more than one reactant. Questions? Understand that a rate law, shown here, differs from the rate expressions that we wrote at the beginning of the lesson. This one has reactant and product in it. This one, concentration of reactants only. Rate laws also have K. The exponent is the order with respect to that reactant, and it helps describe how altering the concentration of the reactant affects the rate. On your classwork, in regard to what we've done, which I don't think you have yet, right? You can, these two problems, numbers 5 and 6, okay?